In this video, we are going to be looking at a few more exponential applications. So, an insect colony with an initial population of 100 doubles every day. So, we start off with our typical let statements. So, we have population. So, let P represent population. And we know it's doubling every day. So let D represent number of days. So when we put it together, we have P at D. The initial population is 100. Because the rate is doubling, then we just have 2 for the base. And to the power of D, because it doubles every day. Not every 2 days or 3 days. If it had been every 2 days, then we would have D over 2. Next, we need to graph this relation and state if it's a function. So I'm going to start at 100, which we could say is roughly here, so on day 0. In 1 day, it's going to double to 200. So maybe like that. Then the second day, it will be at 400. And then doubles again to 800, then 1600, and then 3200, and then we're off the page. So let's just connect the dots and put an arrow at the end because this will continue growing. If we look at this, this is a function because every day has only one possible population. Yes, because every independent variable, so every D, has only one dependent variable, so P value. All right, so what type of sequence is this? Well, because we have a exponential function and we see that the growth rate is 2, that should make us think of a common ratio, which means this must be a geometric sequence. So geometric because there is a common ratio of 2. Okay, so next we have to state the domain and range of the function. So for the domain, we have the number of days. So days is an element of all real numbers, but the number of days have to be greater than or equal to 0 because we can't go back in time. And then for our range, we are dealing with population. But population, you can't have half an insect, so it is going to have to be an integer. So P is an element of all integers such that our population is greater than or equal to 100 because that was the initial population. Okay, if this trend continues, predict the population in 2 weeks. So first of all, 2 weeks means that the number of days is 14. So now we can just evaluate P at 14, which means we're going to do 100 times 2 to the power of 14. And when we do that, we should get 1,638,400 insects. And then we'll put a little therefore statement. Therefore, the population will be 1,638,400 insects. Okay, if this trend continues, when will the population be 102,400? So we're going to set our population equal to this value, and then we are just going to solve this exponential equation. Now, when we divide both sides by 100, we're going to get 1,024. And this, we can actually get a common base of 2 in this scenario. We don't have to do that little log shortcut. Now you totally can, but this 1024 should be a little bit familiar from your exponent table. So 2 to the power of 10 is actually 1024. So we can say 2 to the power of 10 is equal to 2 to the power of d. And then we can set our exponents equal to each other. So that means that d equals 10. So therefore, in 10 days, the population will be 102,400. And there we are. Let's try another example. The population of X town is currently 1,200 people and is increasing at a rate of 10% every 5 years. So that's something we should remember. Predict the population in 30 years. So first thing we should do is set up our equation, and then we can deal with that prediction. So we are dealing with population, so let P represent population. And the population is increasing every 5 years. So I'm going to say let T represent time in years. So then we can have P at T equals, our initial is 1200. Our rate is growing by 10%, and 10% is 0.1. So if I add 0.1 to 1, then my base should be 1.1. And then it's going to be to the power of t over 5, because we have to show that that rate is being applied every 5 years. If we didn't put the over 5, then it would mean that it's 10% per year, which it is not. Now we can do our prediction, and we can put 30 in for time. So 30 over 5. So if you simplify that fraction in your exponent, that would be 6. So that means that the population increases by 10%, 6 times in that 30-year span. So when you plug this into your calculator, you are going to get a decimal, and it's going to be approximately 2,125.87. Now, obviously, you can't have 0.87 of a person, and typically we would round up, but for exponential, we would round down to 2,125 because you can't just create that 0.13 of a human. So we have to round down because that's the number of full human beings we would have. So therefore, in 30 years, the population will be 2,125. Okay, let's try a half-life example. A radioactive substance has a half-life of 5 years. Initially, there is 100 milligrams of this substance. Write an equation to model the situation. So, of course, we're going to start with our let statements. We are dealing with mass and years. So, let M represent mass, and our mass is in milligrams. And let T represent time in years. So that means we have M at T. The initial mass is 100. It is a half-life, so my base will be 1/2. And that half-life applies every 5 years. So for my exponent, I'm going to have T divided by 5. Now it says sketch the relation. Is it a function? Explain why or why not. When I do my sketch here, I'll have number of years on the bottom for my time, and I will have my mass in milligrams on the y-axis. I know I'm going to start at 100, and then it's going to decrease. And I do want some accuracy here. So in 5 years, so let's say 5, it will be half of that, which is 50. And then another 5 years, it'll be half of that. So that is in 10 years. And it will be 25. So just a little bit of accuracy, and then you can do your decrease. And now it asks, is it a function? Yes, it is, because for every year, there's only one mass. So yes, each T has only one M. So the mass can't be two different things on a particular year. Okay, state the domain and range of the function in this scenario. So for our domain, we're dealing with time. So time is an element of all real numbers, but it does have to be greater than or equal to 0. And then for our range, we're dealing with mass is an element of all real numbers. And the mass is going to have to be greater than 0, but it's not actually going to reach 0. And then less than or equal to 100 because that was the initial value. Okay, if this pattern continues, predict the amount remaining in 200 years. So why don't you pause the video here and try this example on your own. You are going to get a really tiny number, so you might have to do something like times 10 to the power of something and just round to 1 decimal. So pause, complete it, and then come back. Alright, so when you plug 200 in, you are going to get a really small number. Depending on your calculator, you might see the times 10 to the negative 11, or you might see e negative 11. That just means the number is actually 0. And then add 10 zeros, 91. It just means you're taking that decimal and moving it to the left 11 times because your exponent is negative. And there we go, 9.1 times 10 to the negative 11 milligrams. And then you'd want a therefore statement. I just can't fit it here. Okay, for E, when will there be 6.25 milligrams left? So we're going to set our mass equal to 6.25. And when you divide both sides by 100, you're going to get hopefully a familiar number that you know what it is as a fraction. If you know what it is as a fraction, that's wonderful. So you get 0.0625, and maybe you know that that's 1 over 16. If you don't, it's okay. You can still use the log trick here, but because I have put it into 1 over 16, 16 is familiar to me because I know 2 to the power of 4 is 16, so I can get a common base of a half by doing a half to the power of 4 equals a half to the power of t over 5. And of course, you could have also done the log trick and done log of 0.0625 divided by log of 0.5, and you also get 4. So you know that the exponent t over 5 should be set equal to 4. And then I'm going to put the 4 over 1 and cross multiply to get 20 years. So then I would write a therefore statement. Therefore, in 20 years, there will be 6.25 milligrams left. So this scenario kind of includes everything in that you're creating an equation, you're talking about domain and range and your sketch, setting some time equal to something, setting your mass equal to something. So you're doing both simplifying and solving in this type of question. All right, let's try the next one. The population of a town in 1980 was 24,000. In 1990, the population was 29,000. What is the yearly percentage increase in the population of the town? Then write the function that models this situation. So I'm going to look at 1980 as my initial year and my initial population. So I'm just going to start off by writing what I have in my equation, but of course I will begin with my let statements. So let P represent population and let T represent number of years since 1990. I can't just say it's the number of years because then you might think that you can plug in 1990 in for T, but it's the number of years after 1980 because that's going to be my starting point. So my equation would be P at T equals, the population in 1980 was 24,000. We don't actually know the rate, so I'm just going to write B for base to the power of T. So all I know is the initial value. Now, I can use this 29,000 in 1990 as a coordinate. I know 10 years later, so T is 10, the population was 29,000. So P is 29,000. So I have a coordinate that I can actually plug in for the population and for time, and then I'm just going to solve or isolate for B to get that yearly increase. So 29,000 equals 24,000 times B to the power of 10. And just like when we solve a regular exponential function, I'm going to divide both sides by 24,000. And when I do that, I'm just going to keep it as a fraction, but 29 over 24 because the zeros cancel out. And now, this isn't actually an exponential function because my variable is not in the exponent, but I can get rid of that 10 very easily. I can either take the 10th root of both sides, but not all calculators have that. So instead, I'm just going to raise both sides to the power of the reciprocal, which is 1 over 10. And when I do that, I get a base that is approximately 1.02, which means it was a 2% increase. And then because we now have our base, we can put that into our equation. I'm just going to put it right here. So P at T equals 24,000 times 1.02 to the power of T. So sometimes you're not given all of your information, but you will be given an additional coordinate that you can use to solve for your unknown. All right, let's try this last one. The value of a car today is $3,800. If the car was purchased 7 years ago for $19,500, determine the depreciation rate or the decay rate of the car's value. Then write the function that models this situation. So this is very similar, but now I'm going to use the starting value of the car, so 7 years ago, as my starting point. So I'll say let V represent value and let T represent number of years. So then I have V at T equals, the initial value is 19,500. We don't know the depreciation rate, so I'll write B to the power of T. And then we know that 7 years later, so in 7 years, the value drops to 3,800. So I want you to pause the video, sub this point in for the value and the time, and then solve for that base to get the depreciation rate and the final equation. All right, so when you plug your value in and you divide both sides by 19,500, again, I kept it as a fraction so I don't lose accuracy. So I have 38 over 195 equals b to the 7. And to get rid of that exponent, I'm just going to raise both sides to the power of 1 over 7. And when I do that, I get approximately 0.79 for my base. So if I want to find my rate, if I can't see it right away, I can do 1 minus 0.79 to see how much is left to get to a full 1, and I get 0.21, which means the depreciation rate is 21%. And then I can just take that base and plug it in for B to write my final equation for this. And then I can do whatever I want with this after. I can predict what the car's value is after 2 years, or when its value reaches the halfway mark, or anything I want.